Section 12.6 Triple Integrals in Cylindrical Coordinates, video number 2. We're about to see why cylindrical coordinates are called cylindrical coordinates. I want to show you some special graphs in cylindrical coordinates. All of these equations are pretty small and all involve some sort of a constant, which we're going to call k. The reason I want to show you these graphs is twofold. Number one, to show you why they're called cylindrical coordinates, and number two, when you're integrating a triple integral over a solid, there are some boundaries that define the solid that are easier to represent in cylindrical coordinates. And these shapes are these graphs that I'm about to show you are the graphs that you should be on the lookout for when you're considering to yourself, should I integrate in cylindrical coordinates? Let's start with the equation r equals k. Now what does that mean in terms of cylindrical coordinates for the radius to be constant? That means that down here on the xy plane, before I do any traveling out whatever the radius is, I'm allowed to rotate however far I want. My angle has no restrictions. I can rotate a complete revolution forwards, backwards, however far. The only restriction is that when I'm done rotating, go out r. So let's pretend that this is r, and we'll measure that over here also. Then if the radius is constant but the angle can be anything, then in the xy plane, my graph looks like a circle. But it doesn't just look like a circle, it is a circle. And remember, all this that I've just drawn is still on the xy plane, so let me shoot the x-axis back in the negative direction, put a mark here on the x-axis and say r, and then shoot an axis in the negative y direction, and then where it crosses the negative y-axis, I should put negative r on both the negative x and the negative y-axis. So in the xy plane, the graph of r equals k is just a circle centered at the origin with the radius of r. Now, what does the equation stipulate about z? Nothing. It says z can be anything. So after I'm done rotating and stop somewhere in the circle, I'm allowed to go up or down as far as I want. So anywhere in the circle can shoot straight up or straight down. And what we end up getting is a cylinder. So let's do that to give it some depth. There we go. Maybe I don't know. All right. So the graph of r equals a constant in cylindrical coordinates is a cylinder. So any of our graphs, any of our solids that are bound by cylinders, we should consider using cylindrical coordinates. The cylinder is really easy to describe in cylindrical coordinates. Now, what does the graph of theta equals a constant look like? Well, theta measures how much we rotate. The equation says nothing about the radius or about the z. So as long as we rotate the correct amount, so we'll just call it theta, and drop a line there. And then we'll shoot it back as well, because it doesn't say the radius can't be negative. It doesn't say anything about the radius. Then we can rotate, go however far out we want, and then the z can be anything, so we can go straight up or straight down. Let's just go up for the sake of simplicity. We end up getting a plane. It's almost like a guillotine blade that just drops straight down and cuts space. Let's draw that a little bit more vertical. There we go. So, and I meant to write this back over here. R equals k is a cylinder. Theta equals k is a plane. And let's be more descriptive. It's a plane through the origin, parallel to the z-axis. Because at any point in the xy plane, you can go straight up or down, and that line would be parallel to the z-axis. So if you can just imagine a plane like this, it's just rotated whatever the angle theta is. So what is the graph of z equals k? Well, this one's pretty easy because it's the same thing as if it were in rectangular coordinates. The equation z equals k says nothing about the r and nothing about the theta. So that means in the xy plane, I can rotate as much as I want and go whatever radius I want. So in other words, I can go anywhere in the xy plane I want. But when I'm done doing that, I need to go up k. So all the points that are up k represent the graph of z equals k. So look, we have a plane that is parallel to the xy plane and crosses the z-axis at K. So it's a plane parallel to the xy plane. Okay. You know what? I want to go back to the theta equals K and re-describe what the graph looks like. What I wrote isn't wrong. There's just a more succinct way to describe it. Because this plane is defined by only rotating, but the radius can be anything, that includes the radius being 0. And then we can go up or down as much as we want. So this plane must contain the z-axis, and that's all we have to say. It's a plane that contains the z-axis. It's not just parallel to the z-axis, it flat out contains it, which kind of forces it to be parallel to the z-axis. And I got a dangling open parentheses here, that's going to bother me. All right, so let's take a look at one more equation, z equals kr. Now, way back in the college algebra days, you saw something similar to this that would look like y equals mx. Oh, I'm sorry, were you expecting the plus b? Sure, that would be the intercept, but in this case, the intercept is 0. So we should get a line, sort of. Think about what this equation says. For example, let's pretend that k equals 1. It says nothing about the angle, so I can rotate as much as I want. And it really doesn't say anything about the radius as a value, so the radius can be anything. But once I travel a certain amount, I have to go up k times r to get the z. If the k is 1, that just means whatever my radius is, I go up the same amount. If the k is 2, that means whatever my radius is, I go up twice as far. Or whatever the k is, it just tells you how many radii you go upwards after you've decided on some angle, which is whatever you want, and then travel a radius, which is also whatever you want. If this sounds familiar, it's almost like if we had an r-axis and a z-axis, whatever the r is, let's say the r is 1, then we would go up k, because k times 1 is k. That looks a lot like slope. In fact, this is slope. So we would just get a line that looks like that. But we don't have an r-axis, so to speak, so we could define one by just saying rotate whatever angle you want and then set up your r along that axis. So if you can imagine any plane containing the z-axis, then in that plane we would just draw a line of slope k. So what would that look like? Well, think of it this way. If the radius was 0, so would z, so I would land right there. If the radius is 1, all the z's would equal k. So if I had a circle of radius 1, then it would go up k units. And if I had a circle of radius 2, it would go up twice as far and have twice as large a radius. So let's see if I can do this. Of course I can. It's a cone, but it's not just that. This is technically half a cone because a cone has 2 halves, top and bottom. Let's see, we'll do it like that. So the graph of z equals k times r is a cone. And algebraically speaking, a cone is both halves of this, not just the top. I know most of us think, oh, an ice cream cone is the top half. Mathematically, it's both halves. So it's cone. And the k is basically the slope of the line that determines the cone. So the bigger the k, the steeper the line, the skinnier the cone. The smaller the k, the less steep the line, the flatter and wider the cone. So we got 4 shapes that we can easily describe in cylindrical coordinates. A cylinder, hence the name. A plane that contains the z-axis. A plane parallel to the xy plane. And a cone. So anytime you're doing a triple integral, and your region is bounded by one of these shapes, you should consider using cylindrical coordinates. That, and of course, the structure of the integrand, which might say, hey, use some conversions to make this integrand easier.